So good morning. Welcome everybody to the presentation of my work entitled Application of an Optimization Algorithm to Reduce Crosstalk in Voltage Feedback Method. What we're doing here today is solving a certain problem that resistive sensor arrays have, which is called crosstalk, and we're going to solve it by using an optimization algorithm. So this is the index we're going to follow today. First, we will begin with a brief introduction on resistive sensor arrays. Then we will explain the problem of crosstalk. Then we will be solving the problem of crosstalk using an optimization algorithm in the voltage feedback circuit. Then I will explain some experiments we've carried out by means of simulations in Python. And finally, we will present the results and we'll be drawing some conclusions. So let's get to it. First, what's a resistive sensor array? A resistive sensor array is simply a way of handling several resistive sensors at the same time. These sensors can measure any type of variable, for example, temperature or air flow, like Ethan mentioned before, or pressure, for example. So this is a very efficient way of connecting the sensors because you have some values which belong to all of the sensors at the same time and rows that belong to all of the sensors in the row at the same time. So this would be an example of a resistive sensor, which for us is going to be just a resistance. And these are switches, which are the multiplexers and multiplexers, which are used to select one row and one column, and in the intersection of this row and this column, that sensor is going to be read. So this is a very efficient way of reading sensors, but it has the bad counterpart of crosstalk, which comes from this readout system. So let's take this readout circuit, for example. And I'm going to explain what primary crosstalk is. So in this case, for example, to the voltage divider on the outside of the matrix and to ground. So we expect that the current in this circuit only flows following the green arrow. This would be our desired behavior from the circuit, but it turns out that this is not true. And there are other sneak paths of the current that depends on the value of the rest of the resistances, which finally turn out in the effect that the red sensor from the outside is not the desired one, it's not R2B, but an equivalent resistance all of the existing paths of the current. So this problem has been very frequently addressed, and several approaches have been developed for this purpose. In the first place, we have the hardware approaches, which involve adding blocking components. Basically, what they do is blocking these strange currents from non-desired, or designing better readout circuits, which are applied to the outside. We will be breaking them down soon. Or approaches involve software post-processing algorithms like the fixed point or other optimization algorithms, like the ones we're going to be using today. So let's focus on the better readout circuit. We're going to talk about the zero potential methods. Zero potential method is this side, and the voltage feedback method is on that side. Okay. So in this work, we're going to be working with that one, but the working principles are very similar. In the left case, every sensor is set to 0 volts on both terminals, which means that the current through the sensor is 0 because the voltage at the sensor is 0. In this case, all the columns and rows are set to 0, except has been connected to the continuous voltage. And on the voltage feedback method, it's something similar, but the output voltage is rerouted to the circuit again, and all the sensors are set to that voltage instead of 0 volts. However, the circuits have another problem, which is not shown here, which is called the secondary crosstalk. And this crosstalk does not come from parasitic currents like the case before, and the problem comes from the existence of internal switch resistances, the internal resistances of the multiplexers and the multiplexers, which are painted in red on that side right there. In real components, these resistances are not 0, and this resistance shows that none of the rows or the columns are to the output voltage, so they are set to different voltages. So the problem is not completely solved. This problem highly solves the primary crosstalk, but there's another type of crosstalk, which is this one. So how do we address this one? Because there's no circuit that solves this one. We have developed a optimization algorithm for this purpose, which means that we have to do it in a post-processing way. We have developed an algorithm which iterates the value of the sensors and the value of the switch resistances to match the output, the real output voltages of the circuit. So what are the steps to develop this algorithm? In the first place, we will have to pose the Kirchhoff laws and the circuit equations for the voltage feedback method. Then, what are our variables? We want to obtain the conductances because it's mathematically easier for the equation. The conductances of the sensors and GS, which are the conductances of the switch resistances. Then we have some information from the circuit, which is the output voltage, the readout of the circuit. But it turns out that we have more variables than output red values from the circuit. So we have to add calibration columns, which are columns of resistances of known values, which are sticked to one of the sides of the circuit. And this also provides us output voltages. And with this information, I already have enough output voltages to obtain the equation. And that is the equation proposed here. We are using a least squares algorithm, which is a very popular and general mathematical algorithm, which is formed by two parts. The output voltage is from the circuit, which I am mentioning right now, and then a function of the output voltages, which comes from the algorithm who has been iterating both the resistances of the sensors and the resistance of the switches. So experiments carried out. We have done this experiment by means of simulations in Python, and we have developed two different resistances maps. In the first case, we have a map formed by random resistances. All the resistors have different values between two known bounds, and we will be calculating the mean absolute relative error for the whole array. Another different case, which is very interesting and very studied in literature, is the one different resistor case, in which all the sensors have the same value except for one of them, which is the one the one we're going to be reading. In this case, this is not a mean error, this is an absolute error. And then we are studying different sizes, 4x4, 8x8, 16x16. The 4x4 are these two cases for rows and for columns, in the right. And then different mean switch resistances values, the values of the switches, the multiplexer and the multiplexer, ranging from 1 ohm to 20 ohms in this value shown here. So these are the tables that show the results obtained from the simulations. The first table is for the random map of resistances. So these are mean absolute relative errors, all of them in percentage. And in the second case, is the error only in the different resistor. So the first row is for the non-corrective case. This first row would be the error that the original circuit is going to have because of the existence of this switch resistance. And then our corrected case with the least squares algorithm. Different sizes, as I have explained, different values of the switch resistances. And for example, the basic circuit, the mean absolute relative error for a mean resistance of, a mean switch resistance of 5 ohms is 21.5%, while after correcting, the corresponding error is 0.03% error. And then in the one different resistance scenario for an 8x8 sensor array, the corrected case goes down to 0.1%. So the efficiency of this algorithm is demonstrated. So what are the conclusions drawn by this work? In the first place, we have seen that this algorithm corrects for the original circuit, which was the voltage feedback method shown in tables 1 and 2. It is clear that after applying our algorithm, the error goes down due to the calibration of the internal resistance of the switches. And then we have also compared with some other works in the literature, which propose different methods to us. In the works of 7, the absolute relative error was under 0.5%, while in this work, the error is almost 10 times lower in the worst case. This algorithm has the bad counterpart of, as it is an iterative algorithm, it takes time to process, so it's a little slow in the post-processing, but for non-real-time applications, it's very suitable for the ZPM website processing frequency of 1 Hz when error ask is already known. And finally, we can say that the least squares algorithm is applicable for this circuit as well. Before we applied it to the ZPM circuit, we have applied it to another one, and their results have been with us as well. So thank you so much for listening. Waiting for your questions.